All right, so I'm going to start on page 23 of the handouts, the dot plots. You should have already looked at the previous 4 pages, the frequency, distributions, and histograms, and I will post solutions for those. Make sure that you have already tried to do them yourself first. Dot plots. We've already looked at these. We've already looked at this one. The most important thing about making a dot plot is that this is an x-axis, okay? You can't skip numbers if you don't have data values there. So you have to treat it like an, equally spaced x-axis, and then for each data value, you just put a dot over its value, and if you have multiple values, then you just stack them. For example, there's 2 63s here. All right, so dot plots, pretty easy to make, kind of fun. It only works with limited types of data sets. Stem and leaf diagram. This might be something you have not seen before. This actually separates the digits of the data. Okay, so for example, here are my student ages from last quarter, fall of 2016. The method we are going to use is to separate the rightmost digit of the number from the rest of the digits. The rightmost digits are called the leaves, and then the left digits in this case are called the stems. And when we make the plot, we are going to put the leaves in ascending order. In other words, from smallest to biggest. So my first data value is 19, so the stem is 1, the leaf is 9. Then I have 21 and 21, so I'm going to go a 1 and a 1. So those represent 21 and 21. Then I've got 1, 2, 3, 4, 5, 6 22s. So I got to put 6 2s, 2, 3, 4, 5, 6. Then I have a 23, a 24, 3 25s, 5, 5, 5, 26, 27, 27, 27, and 29. All right, we have 31, 31, 32, 35, 36, 37, 39, 39, 42, 46, 47. Notice that I don't have any 50s, I don't have any 60s, I still have to have the stems there. I'm just going to leave this area blank. And then I have a 70, so I have to put a 0 there. All right, so that is what the plot would look like for this data. From the plot, now you have to kind of turn your head 90 degrees to the right. Kind of imagine that. And you can see it appears to be very leaning to the left. In other words, right skewed. Okay. All right, so there is another technique you can use for stem and leaf, which is called using split stems. You can use more than one line per stem. Okay. So we're going to redo the example we just did with 2 lines per stem. So the first line is going to have leaf digits 0 through 4. The second line is going to have leaf digits 5 through 9. Oh, sorry. I got to snip this so I can make a new plot. Like this. right, and I want to be able to see the data. All right, so again, the first one is 19, so there's a 1 and a 9. '21, 21, 22, how many again? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 23 and 24. But this time then, so the leaves 1 through 4 are going to go on the first line. Leaves 5 through 9 are going to go on the second line. So starting with 25, I'm going to come down here, and I've got 25, 25, 25, 26, 26, 27, 27, 27, 29. All right, 31, 31, 32. And again, now I'm going to come down to the next line to put 35, 36, 37, 39, and 39. 42 is going to go here, and then I come down to the next line for the 46 and the 47. No 50s, no 50s, no 60s, no 60s, no 70s. I'm sorry, I have 70. And again, I have to leave 2 lines for 5 blank and 2 lines for 6 blank. You can't just disregard those if you don't have data. And again, if you turn your head 90 degrees to the right and look, you can again clearly see, oops, sorry, you know what I'm trying to do, that the data is leaning to the left, therefore it's right skewed. In this case, the split stem technique does work better because it spreads the data out a little bit more, and you can get a better idea of what the distribution looks like. All right, so certain plots are only appropriate for certain types of data. All of the examples that we have looked at so far represent univariate data, which is data obtained from observing values of one variable of a population. So now the difference is we are going to look at scatter plots, which use bivariate data, where the data is obtained by observing values of 2 variables of a population. So, and just a note that this actually jumps ahead to section 4.1 in the book. Okay, it's not in chapter 2. So again, scatter plots are used when you have paired or bivariate or XY data. Plotting the data will often reveal whether there is a relationship between the 2 variables. With these types of plots, the explanatory or the independent variable always goes on the x-axis, and the response or the dependent variable always goes on the y-axis. The goal, or our goal here, is to look for scatter plots that either display a linear relationship, a nonlinear relationship, or perhaps no relationship at all between the 2 variables. So down here, for example, this clearly shows a linear relationship. Okay, oops, sorry. Also clearly a linear relationship. This plot, there is a relationship, but it is not linear. The data are not, lined up in a line. Again, here, there is a relationship. It's not linear. Here, the data is just kind of scattered all over. There is no clear relationship at all. So in particular, we are interested in looking for linear relationships. So here is an example. This data is from StatDisc 13th edition, data set number 2. So if you wanted, you could go into StatDisk, you would see this exact data, and you could try to plot it. Let me do this. So this in particular is a scatter plot of height, comma, foot length. I'm just going to abbreviate here. Okay. So the height is the x variable, the foot length is the y variable, and we always say y variable, foot length, as a function of x variable, height. Okay. Looking at the plot, the question down below is, does there appear to be a relationship between the two variables? Clearly, yes. Okay, the variables are kind of lined up in an approximate straight line, which makes sense that as a person gets taller, their foot length is going to be longer. Okay, so yes, there is a relationship between the two variables. If we go on to the next page, earthquake depth as a function of magnitude. This data is different in the 13th edition, so if you want to try to make this plot in StatDisk, you need to go to the 12th edition data sets. It is data set number 16, and this is a scatter plot of, let me just reuse this, magnitude of the earthquake, comma, depth. So in other words, the magnitude is the x variable, the depth is the y variable. Therefore, we would say the depth, y variable, as a function of the magnitude, x variable. In this case, you can see the data points are just completely scattered around. There is no discernible pattern. So no, there does not appear to be a relationship between these two variables. And just a couple comments about scatter plots. We would never talk about a scatter plot as being, say, bell-shaped or skewed. That is a different type of data. That's for the univariate data where you're making, say, a histogram or a dot plot and you're evaluating the shape of the distribution. Scatter plots, bivariate data, it's different. Okay, we are looking for a relationship. We're not looking for the shape of the distribution like we were before. So what we want to do, we kind of looked at one plot, we said yes, a relationship. Now we looked at this plot, we said no, no relationship. What we want to do is quantify those. We want to quantify and come up with a more formal method for testing whether there is a correlation. A correlation exists between two variables when the values of one variable are somehow associated with the values of the other variable. And in particular, we want to quantify the linear association between two variables. So in order to do that, we're going to calculate something called the linear correlation coefficient. The linear correlation coefficient, and it is a lowercase r, the letter R is the symbol. It measures the strength of the linear correlation between paired data in a sample. So again, that's referring to XY data. So how to interpret this linear correlation coefficient? The value of R is always between -1 and 1. Tell you what, I'm going to go ahead and do this so I can write if I want to. So in other words, -1 is less than or equal to r, which is less than or equal to +1. The greater the absolute value of r, the stronger the linear relation. In other words, the closer r is to -1 or 1. The strongest linear relationship is indicated by a correlation coefficient of either exactly -1 or 1. So in other words, if the absolute value of r equals 1, that is a perfect linear relationship. The weakest linear relationship is indicated by a correlation coefficient of r equal to 0. If it is positive, it means that if one variable gets bigger, the other variable tends to get bigger also. In other words, the line is going up. It has a positive slope. A negative correlation means that if one variable gets bigger, the other variable tends to get smaller. In other words, the line goes down. It has a negative slope. The correlation coefficient is not designed to measure the strength of a relationship that is not linear. And also just a comment that R is very sensitive to outliers. All right, so just some examples showing you linear correlation coefficients. So this one here is a maximum positive correlation. This is a perfectly straight line. This corresponds to R equals 1, +1. On the other hand, the one just below it, minimum negative correlation. Again, these are perfectly in a straight line. This corresponds to R equals -1. Up here, these are fairly well going up in a line. You can clearly see the trend. The points are fairly clustered. It's a pretty strong correlation. This corresponds to R equals 0.8. This one down here, clearly there's a negative linear trend, but the data is more scattered than the example right above it. It's looser. This corresponds to an R of -0.43. This one, data is just totally scattered about, kind of like the earthquake example. That corresponds to an R equal 0. And this one, to compare it to an R of 1, these are perfectly in a straight line except for this one outlier. And it does have a strong effect because then R is equal to 0.71. So for example, here are the two plots we already looked at. The foot length as a function of height and the earthquake depth. So just take a minute and look at the graph and estimate. What do you think the value of R is for each of those? Pause this if you want to actually take a moment and do that. Because right now, then I will tell you, first of all, if I were looking at this one, I might estimate, I don't know, 0.8, 0.85. It's a pretty tight linear correlation. And in fact, the calculated R is 0.842. Over here, estimated R, maybe 0. It's totally scattered. So something very, very close to 0. And it is, in fact, if you calculate it, it is equal to 0.027. So down here, again, pause this for a moment. This is just matching. Pick the correct value of R that matches with the given graph. Okay, I'm going to give you the answer right now. Obviously, this is the tightest one. It corresponds to the 0.95. Clearly, this is the only negative one. It corresponds to the negative 0.61. And then just using the process of elimination, this correlation is clearly tighter. It's more of a straight line than this one. This is looser, more scattered. So therefore, this one corresponds to 0.83. This one corresponds to 0.39. All right, so let's look at a series of steps to actually formally evaluate the correlation. The first thing you want to do is just explore the data, as we've been doing, by making a scatter plot first, because that will give you an initial idea of whether or not there is a linear relationship. Second, you need to compute the linear correlation coefficient R based on the data. And then third, you're going to compare that calculated value of R to a critical value of R. And I will show you how to look those up. So here is how to calculate R. There's this formula, or there's this formula. There's actually many different forms of the formula. They are all equivalent, and they're all pretty equally scary looking. Fortunately, we are not going to calculate it by hand because it is extremely tedious, and there's no need to calculate it by hand because we can use StatDisk to calculate it for us. So that is what we're going to do. So for example, I am in, this is from the StatDisk 13th edition data file. I've opened the foot length height file. What did I say? That was data set. Yeah, data set number 2 if you want to try this. And then at the top of the StatDisk, just go to Analysis, Correlation and Regression. We plotted foot length, so that was my y variable, as a function of height, so that was my x variable. And then just always leave this at a significance of 0.05. Hit Evaluate, and then it will give you the results. So what we want to look at here is right here. You see this line? Correlation coefficient R, 0.842037. So that is the calculated value of R, and that seems to match, what we thought just by looking at the plot, that it was pretty much in a straight line going up. Okay. Right below that, it will give you the critical R. Okay, so this is the critical value that we're going to compare our calculated value to. And the critical R is always plus or minus. So in this case, it is plus or minus 0.312. The critical value depends only on the sample size, how many data values were there, and the confidence level. And we're going to assume a confidence level of 95%. The sample size here, it's given right up here, n equals 40, meaning there were 40 pairs of XY data. Now I'm going to come to the next page and then we'll come back. On the left, table 2, this is from our book. Okay, this is giving us the critical values for the correlation coefficient, R, and n is the sample size. So the problem with the table in our book is it only goes up to 30. So that is why I included another table from a different text, which goes up to higher sample sizes. So on that table, if you come down to 40, and what you want to do is just X out this column. Okay, we're not going to use this column. We're only going to use this column, which corresponds to the significance and or confidence that we want. So for a sample size of 40, the critical value of R is 0.312. And really what that means is plus or minus 0.312, because R could be either positive or negative, depending on whether your line is going up or whether it is going down. And like we see, the 0.312, that's exactly what StatDisk tells us. So how to use those numbers then to actually test? Let me get a new snip going here, like this. Sorry, this seems to be a little delay every time I try to do this. There we go. Okay. So find the correlation coefficient, find the critical value. Like we said, if R is -1 or +1, that is a perfect linear correlation. Okay? If R is 0, that's just totally scattered data. No linear relation at all. The R that we just calculated was 0.842. So that is up here, very close to 1. Okay? And if it is close to either 1 or -1, that indicates that there is a linear association. Okay? Specifically, we can label our critical values. Our critical R is plus or minus 312. So that is right here. Okay? 0.312. And then I'm also going to go ahead and label it on the negative side. Negative 0.312. So what this says is, if I calculate R based on my data, and if it is inside these critical values, if it is anywhere in between the negative and the positive critical value, that means it's close to 0. It's close to 0, which means the data is scattered. There is no linear relation. On the other hand, if it is outside of the critical value, okay, and in this case, ours is, it's close to 1. Or if it were negative, if it were down here, it's close to -1. So either way, if it's up here or if it's down here, then that means that there is a linear association. All right, so you basically want to calculate R, compare it to the critical R, and see, is it inside the critical value, which means no line, or is it outside of the critical value, which means there is a line. All right. All right, so that was scatter plots. A time series graph is basically just a specific kind of a scatter plot where the x-axis represents time. It can be whatever, months, years, days. The y-axis represents the data at that time. And these are very useful because they reveal any data trends over a period of time. So just here's a recent example I took straight out of Gallup. It was a report on 5 key findings on religion in the U.S. And basically showing the general trend over time, this goes from 1938 to the present, is that far fewer people are members of a church or other religious organization. I did notice, however, that this is a perfect example of a truncated graph because they started their y-axis at 50%. Really, they should have started it at 0%. By doing it this way, it makes the drop look much more dramatic, right? Alrighty, and finally, just a summary of organizing data. We started by talking about qualitative categorical data. We use that to make a frequency distribution, a relative frequency distribution. Remember, we did that with the ethnicities of my former students. Then you can use that to make either a pie chart or a bar chart. And again, this is non-numerical data, therefore you do not consider the distribution shapes of this data. You would never talk about it as being left skewed, right skewed, or bell shaped. That doesn't apply. All right, then we went on to quantitative or numerical data. And first, the univariate data, where there's just one variable for each observation. And again, we started by looking at frequency distributions, relative frequency distributions. We used that to make a histogram. We looked at two different cases, the discrete data and the continuous data. We looked at dot plots. We looked at stem and leaf diagrams. For all of these types of graphs, you can analyze and describe the shape of the distribution. Skewed, uniform, bell-shaped. Then we went over the quantitative, again, numerical data that was bivariate. This was the XY data. And that consists of scatter plots and time series plots. In this case, you want to analyze the plot to see if there is a relationship between the two variables. It is not appropriate here to discuss the shape of the distribution. Again, you would never call it skewed or bell-shaped. You're just looking for the relationship between the two variables. Okay, I do want to go back briefly and just do a little StatDisk demo of the scatter plots and the correlation analysis. So I've just got StatDisk going here. I'm just going to open up, so this is the 13th edition, the foot and height data. So this was the plot we looked at earlier. I'm going to go data, scatter plot, and we want our y variable to be the foot length. So that's column 3. So foot length as a function of height plot. I mentioned in the assignment file I would like you to get rid of this green line. It will automatically plot this regression line whether or not there is a linear correlation indicated. So down here under regression line, just uncheck that. And then sometimes you have to fiddle around and check it or uncheck it a couple times. It appears that the options for labeling the scatter plots do work. So for example, I'm going to type in foot length as a function of height. I discovered, I'm pretty sure that as soon as you finish that, now I'm going to hit the enter key. Boom, there is my title. So this is great because it's much easier to do it. Height in centimeters, enter, and foot length in centimeters, enter. So that is how you do the scatter plots. And like we said when we were looking at this, we estimated an R value pretty close to whatever we said, 0.8 to 0.9. I'm going to go to analysis, correlation and regression. Again, I'm going to leave that significance. I've got foot length and height. Evaluate. There's the numbers we looked at before. So that will calculate the correlation coefficient R. It will tell me the critical value. All right. And then we have to know that, okay, this indicates that yes, there is a linear correlation because R is closer to 1 in this case. It's outside of that critical R. Let's go to the other one, and this I have to go back to the 12th edition because they changed the earthquake data down to earthquake measurements. And in this case, we had plotted data scatter plot, the depth 2 as a function of magnitude plot. Again, I'm going to get rid of that correlation line. Okay, and again, I could add in the titles. I'm not going to do that right now. Analysis, correlation and regression. Same thing, depth as a function of magnitude. Evaluate. This is what we saw before. The correlation coefficient R, very close to 0. It's inside the boundaries of the critical value, which is plus or minus 0.2787. So therefore, that indicates that there is not a linear relation. And don't forget, if the trend, if the data is going in a downwards pattern, this is not, but imagine if it were, then that is going to result in a negative correlation coefficient. So you just have to keep that in mind.